experiment number 1, the kinetics lab, and you will find that right here under module. Okay, and you'll find that in this right here, week 5, already in our 5th week. Okay, so let me close this because we're done with these sections. The first part, of course, is just the lab manual write-up. Okay, this just describes the entire experiment, so you don't have to like refer to the lab manual overall. This right here is the grading rubric, and I've tried to make it easier for you so that you know when you start writing what you're going to be graded for the content. So it's right here, and I put it up front rather than at the last page. That way you'll be sure to use it. Okay, you'll be sure to use it. So this is worth no points. It's just information. Let's go to the next one. The next one is your introduction. Okay, and again, under student view, you will see this submit assignment. You click on the submit assignment, you get this editor, and then you start writing your intro. Okay, let me get out of student view. So again, it gives you the introduction to the experiment, the materials that's being used, and the pre-lab questions and the procedure, because all of this is going to be included in your pre-lab write-up, right? You need to give an objective, make sure it's in your own words. Look at what I recommended in activity 4A and 4B. Got to say something about what you're going to be doing. Got to be saying about what chemicals are being investigated and what experimental technique you guys are going to be using, or the equipment. Those things is what I'm looking for in your objective. Then some background information. You're using Beer's law in this particular experiment. You got to mention something about Beer's law. Okay, you're looking at the reaction in which methyl Viologen reacts with hydroxide to form this compound right here. This chemical right here is purple. That chemical is colorless. We can abbreviate that reaction via this shorthand nomenclature. And then you guys are going to be determining the rate law. And the rate law is going to consist of the order with respect to methyl Viologen. And this is how you guys are going to figure out the order with respect to methyl Viologen. And then you're also going to determine the activation energy using the Arrhenius equation. Okay, so that's the background. Read more into that. Maybe you can add more. This is the chemicals that's being used, the procedures right here. Remember, right after the background, you have your procedure right here. And safety is important right here. And then your pre-lab questions comes at the very end. Please keep to the format. Even though it's not written in that order in the lab manual, that's the order that I would prefer. And that's generally the order that most lab experiments are done. You have your intro, background, procedure, safety, and then the pre-lab, the questions. Now, this question right here is a simulation of what you will be doing in this experiment. You guys are going to be monitoring the concentration of a chemical with respect to time. You're going to basically generate a plot of concentration versus time, natural log of the concentration versus time, 1 over the concentration over time, and you're going to see which fits a straight line. So that's what this pre-lab question is. It simulates the actual calculations, the analysis, part of the analysis that you will be doing for this lab, determining the order via graphical analysis. Okay, so that's this part right here. This is the table that you guys, well, the table that you guys are going to be accumulating, I think is right here in terms of, actually it's concentration versus time. And then this is processing the data. Okay, so that's your intro. It's not due till Wednesday. It's not due till Wednesday. Let's go to the next portion. The next portion is your data and observation. I want to talk about this a little bit in more details. Okay, and so I'm going to skip it for now. Let's go to your write-up. Your write-up, processing the data. I tell you how to process your data. Tell you what type of data you're generating. This was also written in your lab manual. And then information that you should include in your discussion, and then the post-lab questions. Okay, so that's processing the data. And this experiment is not due until March 15th. Okay, and that's because this is a 2-day lab. Whole next week, you guys have time to work on this write-up, and then Monday, it's going to be due. Okay, and then it's due until actually the following Tuesday. That's the until date. This is the due date. That's about a week and a half from this Wednesday. Okay, and then this will be a Monday, and then the 16th will be a Tuesday. So if you can't get it in Monday, you still have 24 hours to get it in without penalty. Because I know that you're like me, you'll procrastinate until Sunday night. Let's go back. Let's take a look at the data and information. Before I do that, though, let me give you this right here. Let's talk about this experiment. So this is the experiment that you guys are going to be doing. Then put on this PowerPoint slide. Okay. This right here is methyl Viologen. Something interesting you should know about methyl Viologen is that it is a dye. But if you have blue ink, if you have a pen and you have blue ink, that dye in your blue ink is methyl Viologen. That's the chemical in your blue ink. Okay, and it looks purplish here, but at high concentration, of course, it looks dark blue. And then this actually is the progression of the reaction as it reacts with hydroxide, and it goes from a dark, intense purple or blue to a clear. This right here is the absorption of methyl Viologen. In other words, it absorbs light highest at about 590 nanometers. So what's going to happen is that if we monitor 590 nanometers and watch that absorbance decay, then the decay of that absorbance right here with time is going to give you information about the concentration of methyl Viologen, the initial chemical, with time. So I just want to point that out. Of course, the purpose of this experiment is to figure out the rate law for the reaction of methyl Viologen with sodium hydroxide or hydroxide, and also determine the activation energy. You need to include more, but just to give you an idea of what the overall reaction is. This right here is the chemical reaction that is occur. This is methyl Viologen, also known as crystal violet. Okay, notice this carbon in the center is trigonoplanar. Okay, in its trigonoplanar geometry, all these rings are in the same plane. When all these rings are in the same plane, the electrons, because you guys know about hybridization, you learned that from general chemistry, can hop from one ring to the other. And because you can do that, it makes this particular chemical colored. Okay, it makes this particular chemical colored. It basically means it's violet or deep blue. When you take hydroxide, because you introduce it through sodium hydroxide. You don't introduce hydroxide from an alcohol. Even though methanol is CH3OH, that OH group stays with the carbon because that carbon-oxygen bond is very strong. It doesn't come out. But with a base, that hydroxide comes off readily from sodium and attacks that carbon, and it makes that carbon tetrahedral. When this carbon's tetrahedral, then all of these rings are not in the same plane anymore. When they're not in the same planes, then the electrons can't hop from one ring to the other. That makes it transparent. The energy is higher. Okay, so now it becomes white. So this is the mechanism by which this reaction occurs. And we can abbreviate that as CV, representing this crystal violet chemical, plus hydroxide goes to CVOH. And what we are going to be doing in this experiment is we're going to make the hydroxide concentration so high that when this reaction occurs, the hydroxide is such an excess, it's not going to influence the rate. The rate's going to be influenced by the limiting reagent, crystal violet. And depending on that concentration, the rate will change accordingly. And that's what we will be doing in this particular experiment. We'll make the crystal violet concentration much lower than the hydroxide. Therefore, the rate is a function of the crystal violet rather than the hydroxide. The hydroxide will be what we call pseudo first order, in that it's going to be part of the reaction, but it's not going to influence pseudo zeroth order. It's not going to influence the speed of the reaction. Okay, when we say pseudo, it means like it's a fake, and we're just going to abolish it from our studies. And we can do that because we make the concentration very high. Okay, in fact, 5,000 times higher than the concentration of crystal violet, according to this. So once we do that, then we can take the concentration of crystal violet, and we know the concentration of crystal violet at any point in time because we're monitoring the absorbance. Okay, and we plot the concentration versus time, and it's a linear. It follows a straight line, then it's zeroth order. If we do the natural log of the absorbance versus time and it's a linear graph, then it's first order. And if we do 1 over the absorbance versus time and it's a linear graph, then it's second order. And the slopes here are gives you the rate constant K. So here's a summary of 0, first, and second order. Tells you what the general formula is. It tells you the integrated rate form. That's if you separate the variables and you integrate it, you get these. And then it tells you what graph will generate the information of K. And then you have the half-life equation here as well. This is a pictorial diagram. Now, don't just copy this, okay? But this is a guide as to what's going to happen, how you can do your own pictorial diagram. You have a sodium hydroxide stock. That concentration will be given to you. You've got 2 10 milliliter graduated cylinder. The sodium hydroxide is about 0.02. It'll be more specific when you watch the video. And then you look at methyl Viologen. That concentration, both are 10 mils, but that concentration is about 2 times 10 to minus 5. Okay, what you do is you pour the solutions here, and then you mix it in a beaker. You're supposed to wait a certain amount of time, put in the cuvette, put it in the SpectroVis, and then start recording your data. Okay, and you do that for 3 trials at room temperature, 3 trials at a different temperature, hopefully lower than room temperature, and 3 trials at another temperature, hopefully higher than room temperature. Why do we do it at 3 different temperatures? Because remember, we can't do the Arrhenius equation unless we have temperature data. If we have the rate constant at a certain temperature and we plot the natural log of the rate constant versus 1 over temperature, then the slope times R gives us the activation energy. So that's the reason why we are doing it at 3 different temperatures. Okay. Here's some illustration of when we did this lab a few years ago. Back then, we didn't use a spectrovis. We used something called a colorimeter, but it basically did the same thing. It monitored the wavelength of the light being absorbed. It monitored the absorbance, I mean, at a certain wavelength of crystal violet with time. Okay, and here you can see crystal violet, certainly violet here, but it sort of clears up with time. Here you can see a beaker of ice, and here you can't quite see it, but there's a hot plate back here in which we use to heat up the solution. I apologize for these pictures being grainy, but back then we didn't have high resolution cameras. Okay, here is what you guys are going to be calculating. You guys are going to be collecting time versus absorbance, and then you're creating a column called natural log absorbance, 1 over absorbance, and you're going to have a graph like data like this. And what you guys are going to do is you're going to highlight absorbance versus time, plot it. Then in another plot, you're going to highlight natural log absorbance versus time, plot that. And then in the third plot, you're going to plot 1 over absorbance versus time, and it'll be a positive slope. Whichever gives you the best R, you guys are going to select as that's the one that gives you the best fit. If it's this, it's 0th order. If it's this, it's 1st order. If it's this, it's 2nd order. Now, all your room temperature data should be consistent. If you find in one trial, it's a 2nd order, okay? Not to say that this experiment 2nd order could be, but you guys are going to discover that. Let's say that it's 2nd order in that one trial. Your other 2 trial has got to be consistent. Just because you change the concentrations or you change the time by which you're doing it, it doesn't change the order. The order is fixed, okay? So you can't tell me that trial 1 is 2nd order and trial 2 is 1st order and trial 3 is 2nd order. You can't say that. They all have to agree with each other. Otherwise, the data is not really good, and you need to go back and probably do that experiment if you were doing that experiment in lab. Of course, this is my data, and they all should be consistent with each other. The other thing I want to mention is that it's also true that the order doesn't change just because you change the temperature. Let's say you establish at its 2nd order at room temperature, and then you do the analysis for the low temperature, and you find out that, oh, it's 0th order. No, there's a flaw there. The rate order, the rate law doesn't change just because you change the temperature. The rate law is consistent, whether you have 100 degrees or minus 20 degrees. The rate law is going to be the same. The only thing that changed with the different temperature is K. That's the only thing that changes, okay? So if you figure out at room temperature that it's 2nd order, hopefully you've confirmed that for your low temperature and high temperature as well. Don't tell me that, oh, my room temperature was 2nd, but my low temperature gave me 1st order, because it doesn't work that way. The mechanism is always going to be the same no matter what temperature. The mechanism will give you the rate law. The rate law, therefore, is going to be the same no matter what temperature. Please keep that in mind, okay? So this is how you would analyze for the activation energy. What you will have here, I have 4 temperatures where I did do this experiment. You guys only need 3. The room temperature, the low temperature, and the high temperature, or it could be the room temperature, 1 high temperature, and 1 higher temperature. Doesn't matter what temperatures you have. They just have to be unique from each other, okay? So for each trial, I can get a rate constant for that temperature. So this is the original data, the rate constant and the temperature. Now, and remember, you get the rate constant from this graph right here. This, whatever the slope is, depending on what order, the slope will give you the rate constant. Then you can take that rate constant, put that in a table with the rate constant and temperature. Take your temperature, convert it to Kelvin. It has to be in Kelvin, and take the reciprocal of that temperature. Remember, you're plotting 1 over T. Take your rate constant and take the natural log of that rate constant. Now you're taking the Y, natural log K, and X, 1 over temperature, and you're plotting these two in a graph, and it should be somewhat linear. And that slope times R equals your activation energy. The intercept, okay, if you have this as an equation of a line, the intercept is the natural log of the pre-exponential factor. It's not the pre-exponential factor, it's the natural log of the pre-exponential factor, as you can see from this equation right here. So what you do is you take that value, that natural log of the pre-exponential factor, and you take it to the e power, the exponent, okay? When you take a natural log value number and you raise it to the e power, then it's wiping out the natural log function, and the data, the result from that math is your pre-exponential number. I think a bunch of you tried to do that in the quiz that I gave this past weekend, but you forgot to write down the power, okay? The fact that it's 10 to the 16th. But remember, you want A, because then you ultimately want the A is the pre-exponential value, and that's also important data that you could write down. So that is the processing the data. This is just a guide of what you should have. And this is, I've been hitting you with this since we talked about the notebook. These are the different sections and the order that you should write them. So that's the PowerPoint for this particular experiment. I would normally be giving you this as a pre-lab discussion. I would have normally, if this lab was scheduled for today, I would have given you this discussion last Wednesday, okay? But since we are in a virtual learning environment, then I'm giving it to you now. So when you go to this section in the module, let's go now to the data and observation, because that's where you're going to be spending a lot of your time, at least in the next day or so. If we go to here, data and observation, it's under week 5. It's 01B, 01 meaning experiment 1, B because it's the data and observation, A is the intro, and then C is the post-lab write-up. We click here, you will see the videos. So if you click on this video right here, this is for the room temperature run. Click on that. And then what you want to do is, you see how small this is? Try and get a larger view, oops, by clicking on this right here. Now it covers the whole page, your whole screen. And then go ahead and turn that on, and it tells you right here, experiment 1, part 1, room temperature, kinetics of methyl Viologen. That's the title of this experiment. I basically talked to you guys, this right here. If you didn't hear the PowerPoint, then I give it to you guys here as well. Okay, this is the actual experiment. So what I'm doing here is I'm calibrating. This is a SpectroVis instrument that you guys would be using. Instead of colorimeter that you saw in the PowerPoint, this is what we've upgraded to now that we have a little bit more money with our new science building. But you need to calibrate this spectrometer with water. Okay, so the way you do that, and pay attention to this right here, it's calibrating right now, it's warming up. So this thing is, and then once it's warmed up, this thing will say, okay, finish calibration. So there, and you could always scrub through this, okay, or go back or stop it if you need to do something and look at certain information. So you have the controls in you with your computer to fast forward, slow it down, rewind it, or stop it. Now, what I'm doing here is I'm taking the absorption spectrum of methyl Viologen. Why am I doing that? Because I need to know what wavelength this maximum is, because I need to tell the instrument to sit on that wavelength as I run the experiment. I'm looking at that wavelength. Why there? Because that's the most sensitive wavelength in which it's going to be sensitive to concentration change. So you always want to sit at the lambda max. It's called lambda. Remember, lambda stands for wavelength, lambda max. So the way you do this is you run the SpectroVis and you run the whole thing. And now you can figure out what wavelength that is. And then you find the experiment that you need. This one was just a regular. And then right here, it found that, the program finds that. And then in here are all the wavelengths from 300 to about 1000. It's going to pick that wavelength right here. And now you're going to monitor that wavelength. So that's the calibration process. Okay, we're going to sit at 588. And here again is the super slow-mo of what we just recorded. And that right there, you can see this white bar is going to be the range by which I'm going to be sitting, about 588. Now I'm ready to run the experiment. Prepare the solutions, allow the reaction to react prior to the absorbance reading. You got to let the reaction run a little bit, okay, so that it has time to come together. And once you do that, then you can start monitoring it with the SpectroVis instrument. So here I am. You can see the cuvettes right there. And I put the beakers in a styrofoam cup because the wind drift in the room made the temperature fluctuate. So by putting there, I'm sort of putting some sort of insulator, and I put a temperature probe right here on that solution. That way I know what temperature my solution is going to be. Okay, so you monitor the temperature when the solution is running. And again, you can scrub through this if you get super bored. And then here is the recording. So it's just automatically turned on, and what it's doing is it's recording every 5 seconds the absorbance. And you can see it's already starting to decay. This is the absorbance on the y-axis, and this is time on the x-axis. And here you can read it, absorbance versus time. And every 5 seconds, it's reading something and then it's graphing it. Okay, let's just scrub through this because this is just a practice run. This is just a practice run. And the reason why I made this a practice run is because, let's fast forward. Okay, then I stop at 400 minutes. This is sufficient data to give me an idea of concentration versus time. Then I do the first trial. And if you, again, fast forward this, so this right here is the second trial. It says latest there. Right to the right of that column, if I expand this, will be the previous one. Notice the difference in absorbance. And that's probably because either I changed cuvette or I changed side or I did something different. So the absorbance here is sort of offset, but the slopes are still the same. And the slope of this decay is an indication that the rate of the reaction is consistent with that previous run. Okay, the slope, the way this thing decay, they're very similar to each other. Let's go to trial 2. I'm going to skip ahead and we're going to do trial 2. And look at trial 2. It's practically laying on top of trial 1. So that's even better. Now I've sort of perfected this where I'm putting the cuvette on the same sides, and I'm pretty much consistent in terms of making sure that even the temperature fluctuates, then these things are going to offset each other. If the temperature fluctuate, what will happen is that the decay slope will be different because it's going to be consumed faster or slower. Okay. So let's do trial 3. And again, you can always scrub through. This right here is this is actually what Logger Pro does, is that you see how this is in a computer? It actually records the entire event and then it saves it in the file. So you can actually rerun the experiment with the Logger Pro data set. So this is trial, this is at 25 degrees, this is trial 3, okay? And again, let's start and let's scrub forward. And again, you can see right here, it's sitting on top of trial 1 and trial 2. So for room temperature, the data is pretty good. Trial 1, trial 2, trial 3, practically sitting right on top of each other. And of course, I will show you the towards the end here, you have the whole screenshot of Logger Pro. Right here is the whole screenshot of Logger Pro. Now, if you don't get all of this right here, don't worry about it, because you can download that file. You can download that file. So let's get out of here. And then the next thing I want to do is I want to show you, so that's room temperature. This is low temperature and high temperature. Why is this important? Because what you need to do is you need to maintain the temperature of your solution. The problem is that, let's say that you take your cuvette, and let's say that at room temperature, it's 25 degrees or 20 degrees, and you want to record the, you want to run the experiment at, say, 16 degrees, okay, a little bit cooler than your 20 degrees, 4 degrees cooler. So what you need to do in order to lower that temperature is you need to put it in a cold water bath or some ice, and not so much ice, because then it'll really drop the temperature. And the lower the temperature, the slower the reaction. But let's say we do it at 16 degrees. What happens is that if you remove that cuvette from that cool water and put it into the the spectral vis, I mean, you put it in the spectral vis, it'll start warming up. So it's going to go from 16 to 17 back to room temperature. You can't do that, because then what will happen is that the rate's going to change. So what you need to do is you need to take that cuvette in that cool water bath, put it into the colorimeter for some time, maybe a minute, record the absorbance, and then take it out and then put it back in the solution so that you're maintaining that 16 degrees constant temperature. That means that when it's not in the colorimeter, there is no absorbance to read. That means that the absorbance are going to start to decay, and then it's going to go down to 0 until you put the cuvette back into the colorimeter, then it'll go back up. So that's what you see in the room temp, the low temperature and the room temperature data. So let me just show you that. Okay, again, let me increase that size so you guys can see. This is low temperature and high temperature. And please make note when you're watching this video what the temperatures are. There's 3 trials. The temperatures are going to deviate slightly within like 0.5 degrees from each other, but you can take an average. Okay, again, this is just information. This is now, you can see I've got my styrofoam cups. I'm setting up the data. I'm setting up the instrument. And I believe for this first set of trial, it's water calibration again. You always got to calibrate your instrument. You can see that I'm putting ice, not on the primary cup, but down here in the secondary cup. Because if I put in a primary cup right there, what will happen is that temperature fluctuation will be too drastic. It'll be going up and down. So I actually have the ice down here in the second one, then I cover it. I cover it, okay? It's not very well covered, but it's good enough so the temperature doesn't fluctuate. So here I am preparing the solution. And what I do is I prepare a standard solution here, and I prepare the solution which I'm going to measure. And the reason why I prepare 2 solutions is because I need to try and simulate the temperature, but I can't be putting the temperature probe into the cuvette. Okay, so I just put the temperature probe right here, and hopefully my temperature is constant. That's the hardest part about this experiment. Make sure that that temperature is constant. So again, this is all the prep work just to do that. And here I am just waiting for that reaction to occur. Now I'm ready to run, and notice the temperature. It's right here. Okay, you'll be able to read the temperature in the Logger Pro data. And now I'm going to go ahead and start the experiment. And 23.6, first run. So here it is. And I should be running the experiment right there. Okay, see that this is the absorbance. So I'm changing the scale so it's full window. The temperature is up here because I have a temperature probe in my solution, and then I have my absorbance. So notice that it drops down to 0. Why? Because I pulled out that cuvette from the SpectroVis and then reintroduced it. Then what you will see again is it'll drop down to 0. And then it's when I pull it out. So I pulled it out again. And what I'm actually doing is I'm dumping that whole solution. And then this solution in here is actually the solution where it's running at that temperature. So I'm dumping that whole solution. I'm refilling that in here. And so you can see that what I need to record is data from this point, this point, this point, but not down here, because that's a 0 reading. This point, this point, this point, all along this curve is where I want to get my data from. So it's going to look like this, where you have the absorbance, drops down to 0, and then it gets back up. So let's just scrub through this that way. And this is trial number 2. And again, it's going to be offset. It's not as perfect, but as long as the curvature is the same, you're good. Okay, you're good. As long as that curvature is the same, you're good. Here it's slightly off. Here it's perfect. Here it's slightly off. And again, that has to do with the alignment when you put the cuvette inside. It has to do with the alignment when you put the cuvette inside. But let's move on. That was trial 2. So I can pull data here. I can probably pull data here, definitely. Let's do trial 3. This is trial 3. Again, notice that the curve is consistent with each other. Even though it's offset a little bit, the decay is still the same. And hopefully the temperature hasn't changed from one trial to the other that dramatically. If it's within 0.5, you're good. But those are experimental errors. Okay, those are just experimental errors. If you want to be more precise, you need better instrument. In fact, an instrument where you can control the temperature of the box and not have to keep pulling the cuvette out and putting it in an ice bath or a warm bath. So that's low temperature. Okay, let's do high temperature. Now we put it in warm water. Under here is warm water. And again, I'm trying to insulate it. Let's look at the data. And here you can see that this temperature is 34.3 degrees. 34.3 degrees. Let's move. And the higher the temperature, the faster the rate. So the decay is going to be faster. Okay, the decay is going to be, and this is in fast forward motion. I'm basically just speeding up the my original data so that you don't have to like go through this 3-hour experiment. you can finish this whole experiment within like 15, 20 minutes. So that's your first trial. Let's scrub through and look at the second trial. Second trial again, and notice it's offset again. Don't worry too much about that. What you're looking at is the curvature, and they're consistent with each other. If this thing had dropped like from here to here, where that slope are not parallel to each other, then something would have been wrong. And then let's take a look at the third. And this would be, oops, this is the Logger Pro. This is the third. Okay, you can see 3 sets of plots there. And then I give you a close-up of the Logger Pro data set. And then that pretty much is it. So that's the experiment. And that's why we have it over 2 days, because it is pretty tedious. It is pretty tedious. Let me get out of here and get out of this. Let's go back to, where's my canvas? I think this is it. Let's see, where did I put canvas? That screen went away. Okay, let's take a look at, go back here. And the reason why we need to go back here is because I want to show you the data. So that was the video of the experiment. Now you can download the data. Here we are. Here, okay. Click on data and observations right here. If you click on this, you will see the Excel spreadsheet. But if you click on this, you can actually download that Excel file, and it should be in the Excel format. Okay, this is the Excel format. So this is trial 1, this is trial 2, this is trial 3, and this is for the room temperature. So I gotta take a look at that. But this is an Excel chart. That's for room temperature. This is for low temperature. Okay, this is for low temperature. And notice that I'm just recording absorbance after a certain amount of time, because otherwise you have data overload. This is another Excel spreadsheet for the high temperature. And you always have 3 trials, trial 1, trial 2, trial 3. So you can download that data. I'm not going to save that. And then there's another file here, okay, the Logger Pro. This is the Logger Pro file. Of course, you need the Logger Pro software. And since you are enrolled at Miramar College, you can download that Logger Pro software by clicking on here and download that software here, license download. Okay, so you want to download Logger Pro 3, and the password that you guys will need is right here. These are the different versions, and these are the links. And I think via these links, you don't need a password. So all you gotta do is copy and paste these URL on your browser, and you should be able to get the Logger Pro program. And when you get the Logger Pro program, then you can take this right here, which is the raw data. I'm gonna show you that it's gonna download as a zip file. Open up that zip file. And if you have Logger Pro, you can just click on these things. And you have the original Logger Pro data. Replay of the data, then you would simply click on the data sets here and then do analyze and replay. And when you do that, you should be able to run this program. I'm going to go fast forward here, 45, and then start. And so here would be the data at 45 times the original speed. Okay, I don't want to go 1 time the original speed because it would be too slow. You'd be waiting forever. So if you want to see what goes on, 30 times the original speed will be fine. And you can see the decay. This is for room temperature. Remember, we didn't have to remove the cuvette from the SpectroVis. So that would be run 1. Let me stop here. Let's suppose I want to do run 2. I just need to highlight these 2 columns and then change that to run 2 and then start. Let me see, cancel. You're just gonna have to, here it is, okay? Let's run 2. So you can do that for any of the data that's collected if you've got Logger Pro. So try and get Logger Pro because it's a very useful software, at least for data processing for this particular class. Let's get out of here. You can't just close this. You have to quit the program. But as long as you have that software in, let's take a look at low temperature. Okay, here's the low temperature. And again, if I want to see what's out here, then I can move that, or I can take this bar and extend it. Okay, there's certain things that are hidden. So I'm going to do time versus absorbance. And I'm going to run 2. And let's see how that plays out. You gotta hit replay twice to get this menu. And what we want to do is run 2. And then we want to start. And here you can see, let's move this out of the way, the simulation of how run 2 was recorded. So normally, it's about 8 o'clock now. You would have started this experiment as soon as you walked in, and you wouldn't have been done until 9:30. But that's where you find the data for this experiment. You guys are not doing the experiment. You're just going to use the data to get the information so you can start plotting either the absorbance versus time, the natural log of the absorbance versus time, and the reciprocal of the absorbance versus time. Okay, that's the data that you guys are going to be using right here. And that's the Logger Pro data right here. Okay, or the Excel file right there. That is your data and observation section. This is the video. This is a PDF file. Let me tell you one more thing before we close this section. When you guys are, let's just do, you see how this data set has, if I go down this column, there's over, it's over 600, 700 data points. That's too much. It's way too much, okay? And the reason why it has 600, 700 data points is because I told this, I told the program to collect every 2 seconds. And this ran probably over 1,000 seconds right here. So you have a whole bunch of data sets. So what you need to do is you need to just need 20 good data sets. So what you can do is go along this data set and just select 20 scattered concentration and its corresponding time. That's what I did right here. What I did was I just pulled evenly these absorbance with time. And what I could do now is I can plot it, and there'll be less data set something like this, something like this. And even though it has less data points, it's going to be just as accurate as the one with 600 data set. In fact, it'll be easier to handle. So a trick that you guys can do is that rather than use the whole data set, is find 20, 25 data absorbance versus time that is scattered from beginning to the end, so that you don't have to deal with 600 data points. All you have to do is handle 20, 25 data points, and then it'll be easier to do a linear regression on that. Because what I found out when we first did this with 600, 700 data points is that when you try to do a linear regression, it takes your computer forever to do that analysis, because there's so many data points to analyze and to kind of fit. So by doing just good representative data set, you can shorten that time, and it's cleaner in terms of your overall results. Okay, so I just want to mention that, especially for the low temperature, especially for the low temperature. Let me show you that real quick. You just want to select like 1, 2, 3, 4, 5. Don't take anything here. 6, 7, 8, 9, 10, 11, 12, 13. Somewhere where they overlap, and that's good. And find 20 good data set, because there's a lot of data sets here. If you can find that and then you can plot it, it'll make life easier. Okay, so find one in which all three intersects each other. So from here to here, all three have the same time. From here to here, all three have the same time. From here, not so much. From here to here, all three have the same time. You might scoot over here and pick that one as well, but just find 20 data set for the low temperature. You won't have any problems with for the room temperature. And then for the high temperature, let's take a look at that data set as well. Find where they intersect. Yeah, here you got better range. From here to here, here to here, and here to here. Okay, that's fine. If you get data sets there and you find 20 good, then you don't have to graph everything that you see right here. Just find 20 good data sets, and life will be much easier when you do the analysis. So that's all I have for today. I know that's a lot of information. Experiment 1 is a pretty detailed lab, but you guys all have the knowledge of what you are doing, because we just finished kinetics. Okay, this is where the theory hits the reality. We learned the theory in lecture. You guys are now actually doing the experiment and making sense of what rate laws are, what orders are, and the Arrhenius equation based on these. Next time, I will take a data set, and I will show you how you would be able to fit it through linear regression, do Linus on it, so that you can determine whether it's 0th order, 1st order, or 2nd order. That's what we are going to be doing next time.